In this chapter, we're going to look at the spectral theorem, and we'll do the complex spectral theorem first. So this is where the fields are the complexes. And then we'll come back and do the real spectral theorem at the end, but it actually requires a bit of warm-up work. So the spectral theorem characterizes the normal operators as the ones that for which the vector space has an orthonormal basis of eigenvectors. And so we say the following are equivalent. T is normal. V has an orthonormal basis of eigenvectors of T. And T has a diagonal matrix for some orthonormal basis of V. Now, the equivalence of these two parts right here, B and C, that's actually basically already done. So the equivalence of B and C here, this is 541 just for an orthonormal basis. But in that theorem, it's the same basis that gets used for each one. So if we just add the requirement that both of them be orthonormal, then B and C just follows by the fact that we're using an orthonormal basis in either direction that we're proving it. So there's nothing really to prove there. Now let's look at C implies A. So for this one, suppose that we have the matrix for T in some basis, and that it's diagonal. Okay, so then if we look at the matrix for the adjoint, the matrix for the adjoint is, we saw this is the conjugate transpose of the matrix of the original. So that's going to be the conjugate transpose of A. But then A is also going to be diagonal in this basis, because guess what? When you take the transpose of a diagonal matrix, it's still diagonal. And then any two diagonal matrices commute. So then by the isomorphism between operators and their matrices for a given basis, the operators must commute as well. Okay, so that's the easy one. Now let's look at why A implies C. This is slightly more difficult. So for this one, let's see. So T is given to be normal. That's our hypothesis. And since we have that it's a normal operator, we can invoke Schur's theorem. Which says that there's an orthonormal basis for which the matrix of T is upper triangular. Okay, so let's see. So let's actually do a little doodle. So here's a sketch of what the matrix looks like. So the matrix of T in this eigenbasis looks like, so we've got A11 across the top to A1n, coming down to ANN, and then 0 below the diagonal. Okay, and so then the name of the game is we need to show this matrix is diagonal. Okay, well, let's see. So if we look at what happens when we apply T to the first basis vector, and we take its magnitude, let's say magnitude squared, then this is going to be the same thing that we get from looking at the coordinates. So if we look at MT, and let me not write its basis, I'm just going to call it MT, And then here's my little doodle of what the vector for E1 looks like in this basis. Looks like that guy, right? So now, what happens when we do this multiplication? Well, it's like we put the vector 1, 0, 0, 0, 0, 0 right here. And so when we do this product, we pick up A1, 1. And then when we do the next product, what happens is the 1 up at the top meets up with a 0 out here because it's under the diagonal. And then all these zeros kill off everything else. And that works exactly the same thing for all the others. This 0 kills the 1, and then these zeros kill the rest of the row. So we don't get anything other than that particular 1. So the resulting vector from this matrix product has A1, 1 in the first coordinate and zeros everywhere else. So when we take its magnitude squared, we just get this guy. But we can also do the calculation of what happens if we compute it by using the fact that this guy is equal to the magnitude of when we use the adjoint. So for this one, now we're going to be looking at the matrix of the adjoint in the product. And so this is the conjugate transpose. So now we've got A1, 1 transpose down to A1n transpose, ANN transpose, and zeros up above. And then we're still using this, and we're multiplying this against the same vector, 1, 0, 0, 0, 0. And so when we do this one, now what happens? Well, in the matrix product here, we have, so 1 is going to collect the A1, 1 term for the first multiple, when we do the first row. And then when we do the next row, it's going to get A1, 2, and so on and so forth. So we'll have A1, 1, A1, 2, A1n, all the way down. So now, based on the fact that this one is equal to A1, 1 from the first computation, that tells us that all of these have to be 0 because these are all non-negative terms. Okay, so that tells us that everything up here has to equal 0. All right, and then we just continue on like this. So if we go to the next one, see, okay, so what does t do to the next eigenbasis vector? So then we've got mt times 0, 1, 0, etc. And then this is going to be A1, 2, whoops, kind of wrote that a little poorly. There we go, that's better. Plus A2, 2. And then all the others are going to be 0. So notice right now, let's see, so if I redo the blue vector, so we've got 0, 1, 0, 0, then what happens is this 1 right here is going to intersect with A1, 2, A2, 2, and then 0, 0, 0 all the way underneath that. So all the rest of them are 0. But then let's see, from the previous line right here, we discovered that A1, 2 is 0, so that means that this guy is going to be 0. And then from the other calculation, using the adjoint, zero, 1, zeros. Okay. So then what do we end up with here? We get 0 for the first one, and then A22 squared plus a23 squared, and so on. And since this one has to equal a22 from the original computation, or the first computation on this line, again we get that these ones all have to be equal to 0. And so carrying on in this fashion, we see that ajk is equal to 0 for, well, I guess I can ditch the absolute values, is equal to 0 for k bigger than j. So it's diagonal.